Appreciate it.
Awesome. Now, what we want to do today, I've gotten some requests for some problems with the inequality. So I want to do some more work with that to just get us more into the word problem field like we've done with the symbolic computation, and then start discussing some of the basics of functions just to review that from your college algebra days. So let me go ahead and share my screen. Now, what we want to do in this particular case is consider the following function. And like I say, ladies and gentlemen, when you send me a message from WebAssign asking about a problem and it turns out to be a really, really good one, I will share it in my lectures because that's really letting me know what you need to see. So in this first example, what we have is a function. And I know I haven't formally defined the function, but for now, just think of this as a formula. So we have h of t equals 516 plus 16t minus 16t squared. And what this does is this describes the height of a ball above the ground. Now, when you take your physics classes, and maybe you've already had a good physics class in your high school setting, you will actually derive this formula using some derivatives and integrals. So that will be particle kinematics. Now, let me just make one comment here. T will represent time. And for right now, this could be minutes or seconds or whatever. We're not really worried about that. But when we think about time, it's always non-negative. Lots of times when I get questions about this problem, my students say, well, I know I did this right, Professor Ron, why isn't it working? And so we always have to go back to this. So now here's what the question is. When is the ball at least, and this is one of my favorite phrases in inequalities, at least 36 feet above the ground? Now, think about this. What does at least mean? We think of at most as being like an upper bound, but at least as being a lower bound. So this will help us to write the inequality. So when we see this at least 36, that gives us the inequality. So we have, if you want, we can go ahead and write this in descending order. Negative 16t squared plus 16t plus 516, and then at least greater than or equal to 36. So we think of the 36 as being a lower bound. Now we're going to do some of the symbolic computation. Factoring, as you well know, is a very powerful technique. And so in order to put this in a form that will be much more amenable to solving it, we want to make it more user-friendly. So the first thing I'm going to notice here is everything has a 4 in it. So we're going to do this in steps and take it one step at a time. So first, let's divide by 4 and use some of the properties that we talked about yesterday. So when we divide by 4 here, we get a negative 4t squared plus 4t. And now if we divide by 4, we get a 1, then we have an 11. So that'll be a 2, carry your 3, so we get a 36, so that's a 9. So these are nice, easy numbers. And then, of course, dividing 36 by 4, we get a 9. Now, at this point, what we can do is say, well, it would be nice to have a leading coefficient that's positive when we factor. So we'll do this in the next step. We'll just say multiply by -1. I want you to get some practice with this technique, just like we did with the word problems. Now, when we multiply by the negative, is that going to change anything? Absolutely. It's going to reverse this, right? See, that's what we have to remember. So we're going to get a 4t squared minus 4t minus 129 less than or equal to -9. Now, this might be slow and painful, but this is what gets us where we want to go. Now, just like we did yesterday, we know when we solve these more elaborate inequalities, we need to get a 0. So we need to get everything on one side. So you can just remind yourself by saying we need to transpose. And I know we do that without thinking about it, but it's important to remind ourselves. So we get 4t squared minus 4t. Now, of course, if we add 9 to the -129, that gives us a -120. And now we have the 0. So we need a 0. Again, when we're talking about positive and negative and inequalities, it's very easy to compare to 0. Other numbers don't give us that luxury. Now, of course, we're back to where we were at the top. We have some common factors again, so let's divide by 4. So now just write divide by 4. The key, as in all the problems we do, is to make them as simple as possible. So now that'll be easy. So we get a t squared minus a t minus a 30 less than or equal to 0. So now, at least at this point, if we compare this to this, we certainly like this. So like I said on, on Tuesday, well, at least for part of the lecture I spoke, we see that the process of rewriting the given problem in a more user-friendly fashion is usable. Now we can say, well, let's just try the AC. And this is pretty simple. So we have a -30. Now, of course, the 1 we don't really need, but we can focus on the -30. We can just write that as a -6 times a 5. And if that's the Z and that's the W, we get the -1. So that'll work. Now, this doesn't require the fancy factoring by grouping because we have a leading coefficient of 1. So now we have t minus 6 times t plus 5 has to be less than or equal to 0. Now, when you look at this, and this is what I talked about yesterday, we can do the sign test, or we can use the fact that these are just zeros of degree 1. So I want to keep talking about that because we're going to use that later. Now, for instance, what was that term we had? Boundary values. Well, what's a boundary value? Well, when we look at this, the boundary values are what make this 0 or undefined. Can someone tell me what value of t will make this factor 0? What factor makes this, what real number makes this factor 0?
+6.
Absolutely. Now that you're on a roll, who is that? Who just
Brian
answered?
Lewis.
Brian, okay. What about this one?
-5.
Very good. Well, you get your +6 bonus points.
Thank you.
Now, and please don't keep up with these. These are only to promote goodwill. I don't add them to your grade, unfortunately. I know it would probably be convenient though. Now let's just look at this as a number line. So we have 6 and we have -5. Now, another thing, we can do the test point, and I'm going to do that, but since this is just a simple polynomial, we know that when t becomes arbitrarily large, the values are positive. But since this is a 0 of multiplicity 1, we know that the graph will cross the axis, and it has to do the same at -5, but multiplicity 1 and cross back through. So we're like, okay, that's a good deal. Now, that's just using the polynomial. The other way, when we've got a lot of factors, remember, you can do a little sign test, maybe take a -10 as a test point. Always circle the test point, but leave the BVs uncircled. And the simplest number here is 0. And then, of course, we can take a 10 there. These are not unique, clearly. You pick whatever point you want. And now we'll just go ahead and write t minus 6, t plus 5. This technique always works if you don't like this multiplicity deal. So now when we have the -10 here, replace the t with the -10, that still makes this negative. So we have a negative. And then, of course, the -10 here will still make a negative factor. So we verify that this is a plus. Now the 0 should give us a negative. So when we put in the 0 here, we have a negative. So that's negative. Put in a 0 here, that term or that factor is positive. So overall negative, which agrees with what we've already thought. And then the 10 here, again, plus. I don't care what the actual number is, and you shouldn't either. Please don't spend time on something that's not going to get you anywhere. And then 10 here, that's going to be plus. So we verified all of this. Now, what happens at the boundary values? Well, you know, we're thinking, okay, we can get 0 here. So let's go ahead and figure out where the checks and the X's go. We need either 0 or less than 0, 0 or negative. Well, that's positive. That's no good. -5, 0. Here, less than 0, check. 6 makes it 0, check. But of course, that's positive. So nothing there. Now, when we look at this, we're thinking at least for this inequality, the values that make it 0 or negative live right here between -5 and 6. So for now, let's just say this implies that t lives in this closed interval, -5 to 6. But like I said before, students often send me messages and say, Professor Ron, I watched your smart pen videos and I did it exactly like you do it. I said, but did you answer the question? Here is the key. The time must be non-negative. So we can't include negative times. So we've got to restrict to the non-negative. So this implies choose t in the following set, 0 to 6. So the negative values of t do not correspond to our reality that we have t non-negative. So when we complete the problem, we go from here to here. And this can be, like I said before, it's like when you do the WebAssign and you put in a decimal and they didn't say approximate and they mark it wrong. Or did you answer the question? I am more than happy to send you a message to say your work is excellent. Just make sure that you answer the question. And like I say, if you get to this point, you've done all the work. But again, go back. If WebAssign says, wait a minute, I'm not checking this, the first thing you do is you look for typos. But this is an easy mistake to make. And it's not a major mistake. It's just really making sure that we are answering the problem relative to a non-negative time. But, you know, let's face it, the heart of the problem is here. But like I said before, every step is important. We do good work, so when we get to this part, we actually have something to work with. Okay, so I want this next problem, again, this was important because of this and just the technique of the symbolic calculation. This next problem, another student actually messaged me on the WebAssign, and the comment was, I'm not sure if the math is wrong or if I typed it wrong. But here's one thing I noticed about the work. I knew he had done most of the problem correctly because he had two numbers in the problem in his work when he answered it that actually told me that he had factored something. He just didn't know what to do with it. So I thought this would make a great lecture problem. And here it is. A lot of you may turn out to go into financing. I don't know your STEM majors, but some of you may end up getting an MBA. Maybe you get a STEM degree and then you want to go into business. So for instance, we have the following example from your web assign. We have revenue. So if you've ever owned a business, or maybe you have a family member that owns a business, or you work in a business, revenue is what you bring in. And for this particular problem in dollars, we have revenue is 23x. And where X is the number of units. And in the second part of the problem, they define the cost. Again, these are functions, but now we're just thinking of them as labels. So we have cost, and that's equal to a fixed cost of 2,200 plus 10x. And they give you the numbers kind of unfortunately. They give you this decimal. So we're going to get rid of it and clean up the problem. But 25 over 10,000 x squared. So you're thinking, wow, that, you know, we'll clean that up and clean up the fractions and all to make the problem more user friendly. Again, when we do these types of problems, they will be made or manufactured in such a way that the numbers are good to get you practice with factoring. Now, profit, and this is what the question says, determine the number of units for a profit of at least 5,000, and this number is not very unfortunate, even though it looks, $5,675. So again, there's the at least. That gives you the inequality. So in order to solve this, we just use the basic definition for profit. So we're going to say this profit, as you probably already know, is revenue minus cost. So let's go ahead and write it down. Now, to be a little bit more emphatic here, I'm going to go ahead and write that as a fraction, then we'll work it to reduce. So we have the 23x, and now we're subtracting costs, so we must distribute the negative throughout all of these terms. One common mistake in algebra is that a student will negate the first term and leave the others out. But again, we must write in your notes, distribute the negative. Distribute. It's not uncommon to do this, just like forgetting to reverse the direction of an inequality. So we have minus 2,200 minus 10x minus, and I'll go ahead and write this as a fraction, 25 over 10,000 x squared. And the problem says at least 5,675. Now, at this point, what we want to do is clean this up. So we've got this inequality that looks rather unfortunate. Now notice 25 divides 100 4 times. So that's going to give us a 400. So if we write that term first, we have a negative 1 over 400 times x squared, just reducing that. And then here we can combine these two terms. 23x minus 10x gives us a positive 13x. So we've taken care of all of these. And then we have a minus 2200 greater than or equal to 5,675. So the purpose here of doing the last problem is to help you see that this problem is very similar, even though the numbers are a little bit unfortunate. I say unfortunate because we have to work harder. Now, what I want to do, and this is important, let's go ahead and create the zero. At this point, you can use any order you like, but let's go ahead and first create the zero. So right here, create a zero. Remember, for most of the inequalities, the only way to move forward is to get the zero. And if you don't get the zero, you are clearly making it up because you cannot use the sign test without the zero. So now we have negative 1 over 400 x squared plus 13x minus 2200 minus 5,675 is greater than or equal to 0. Now at this point, if you like, we can go ahead and combine some terms, and then we're going to get rid of that negative 1 over 400, but I'm going to do that last. So now we're just court reporting, and now let's add this up. That'll be a 75, and then of course we'll get an 8, and then a 7. So when we look at this, we can think we're kind of like at this point here, where we have the negative. But we already have our 0 here. So now the best thing at this point would be to retire that negative 1 over 400 and make it into a 1. So take your red pen and just say multiply by negative 400. Okay? Now when we do that, tell me something. What's going to happen when I multiply this particular inequality by the negative? What's going to happen to the inequality? Anybody?
It's going to turn the other way.
Absolutely. That's our theorem. So let's do it. Again, this will absorb. And then we have a 13 times a 400. Now, negative negative is a positive, and we do this symbolically. Please, please do not multiply this out. That's not how I have taught you. And then we do this. Okay? Let me check. Okay, now this is where we say, okay, let me go back here. You're like, can we go back to this problem, please? Okay, now you look here and say, okay, whatever the AC method was, we need to have a Z and W whose sum is -1. Okay, well, let's figure out what this number is and do our factoring. So now remember 4, if you play cards, 4 times 13 is 52. So sorry about the X there, we need an X. So we get 5,200X plus, that math is the most satisfying thing you'll do because it tells you exactly what to write. I mean, if you leave something out, it won't make sense. It's like, wait a minute, what happened to the X? Now, let me give you some tricks here. And this is what I did for the student that asked the question when I responded to his message. we're going to need a Z and a W that have two zeros in them, because when we sum them, or at least have numbers in the digits in the tens that sum to the zeros. So the way I looked at this problem is to say, I'm going to look for zeros. Now, let's go over here and do our factor trees. So we have 7, 8, 7, 5, and then we're going to have a 400. And we're going to work on these and kind of see and use the numbers that we generate to figure out what the Z and the W need to be. Now I'm going to start out really simple. This is clearly divisible by 25 because of the 75. So do a 25. So 25 into 78, that'll go 3 times. Then that'll leave a 37. So 25 into 37 is 1. And then now with the 37, that's going to leave a 12 and a 5, so a 125, that's a 15. Again, when the numbers are easy, we don't have to work so hard. Now we're thinking, okay, well, 25 times a 4 is a 100. That might be something useful. Let's see what we get here. Now let's divide by 5. So division of 31 by 5 is a 6. And then, of course, that leaves us with a 15, so we get a 63. And then now, of course, we can use a 9 and a 7. The reason I'm thinking 9 and 7, because the 4 here times this will give us 100, and then a 4 times a 45 is 4,500, which is close to that. So I want a 4. 4 times 100. Now, that'll give me 2 zeros, and then a 7 times a 100 will give me 2 zeros. And if you add those two numbers, you get that number without the negative. So my techniques work, but you have to do them. So now look at this. Take your red pen or some other color. So we need a 100 right there. We can choose this part. And then that 5 and the 9. So that gives us the 4,500. Now use another color or dot or whatever. And then we have a 100 and a 7. That gives us a 700. When you add these two numbers, what do you get? 5,200. Jackpot. So the idea here is that AC works, but boy, we had to do a lot more factoring here to get it to work. Now notice this can be my Z and W as long as I put negatives with them to give me the negative 5,200. So now I have X, or we have X minus 4,500. These are easy when we have a leading coefficient of 1. We don't have to work as hard. And then X minus 700. And that needs to be less than or equal to 0. Now, I know I keep going back to this, but doesn't this look very familiar? You see, it's the same kind of problem. But what I wanted you to see is that the techniques that we use here are universal. You have to factor when you get to calculus. You have to work with signs. You have to do symbolic computation to make your problems look easy. Because if they're not easy, then you don't know how to move them forward. Now, okay, and I'm so bad with names. Is it Brian? Did you answer the last time?
Yes, sir.
Brian, since you're on a roll, can you give me the BVs here?
It'd be positive 4,500 and 700.
Absolutely. Very good. 4,500, 700. Now, as Brian has said, 4,500 makes this 0, this factor 0, and 700 makes this factor 0. So those would be places where we could possibly have a transition in sign. But you know we are, because these are all first degree. So now go ahead and draw. Same as we had before, 700, 4,500. Now, of course, when you generate your WebAssign, the numbers will probably come up differently, but the technique will be exactly the same. Now, again, when X gets really large, we have nice positive numbers, and then the sign changes, and then it changes again. So this is exactly what we had before. Just remember, when we have zeros of multiplicity 1, that's where we get the cross. If it's multiplicity 2, we'll review this, we just touch the axis. So this is going to help us down the road. That's why I want to talk about this now. Now, if you will, go ahead and just to remind yourself of test points, we could take a 0 here. Here, you know, I don't know, take a 2,000. And here a 5,000. So I mean, once it's this straightforward, I think you get the routine. So now, of course, with the 0 here, we get 2 negatives. So this identifies. With the 2,000, this is negative, but this is positive, so we get the negative. And of course, with the 5,000, both of them are positive, so we get this. Now, again, this mimics the last problem. So now we need equal to or negative. So we have check, 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 X, X. So now, this we don't even have to restrict. This implies that if we want, say we've got our business here, if we want our business to have a profit of at least $5,675, then we need the number of units produced to live here. X between 700 inclusive, so you use a bracket, comma, 4,500. Now, this should let you know as math students, and of course as financiers, you know, you own a business. If you own a hotel, you don't want full occupancy. You're going to lose money. It's so odd. Having a business is a mathematical venture. And if you don't pay attention to the mathematics, the business may not be successful. So there are all kinds of factors at play, no pun intended, factor, when it comes to maximizing profit. And those of you that do eventually maybe take some business courses or eventually get an MBA. An MBA is always a nice degree to have with a STEM degree, because it puts you in the pilot seat. That is, you can have your STEM business and you can run it too. You don't have to pay someone else to run it. That's the thing. That gives you autonomy. So again, ladies and gentlemen, when you work problems like this, make sure to use the symbolic computation, use all of the tricks, all of the algebraic maneuvers that we do to put this in a nice, usable form. If we don't, then, you know, you look at this and stare at it. And I would say this, when the student asked about this question, it might have been the way WebAssign generated it, that was his first question. And then you're thinking, wait a minute, I need to flip through this and find something less difficult. But now that you see how we do it, the method is the same. Even if it had been very straightforward, we still use the same techniques. All the techniques are here. Now, there was another question that a student asked about, and it had to do with absolute value. She said, Professor Ron, I'm not really sure what this question is asking. And I understood what she meant. We talked about the conjunction and the disjunction, but this problem was in reverse. So let's just review this. That is, if C is positive, then we have the conjunction, the absolute value of X less than C. Now, in your WebAssign, you were pretty much going in this direction, where you used this and translated it as the compound inequality, like this. So this is what we call the conjunction, and this is used widely in calculus because it helps us to create symmetric intervals, and that's what I want to talk about. I don't usually spend much time with this, but since I chose some problems in WebAssign that cover it, I need to say more about it, and maybe this will stick with you to calculus. And then, of course, the one that we don't use nearly as much, but it does arise, is the disjunction. That is, now we're going to go in opposite directions. That is, x must be greater than c, or x must be less than the additive inverse of c. So we go in opposite directions because both these will work, because when we take absolute value, we're still going to be greater than c. But this is not connected. This is connected. This is disconnected. And we call this the disjunction. Even though these terms are a little bit considered archaic, I still use them because they help you to give a name to this, which will occur so much in calculus, it's good to have a name for it. Now, I'll do an example, but I want to give you a little algorithm. Say, for instance, the question, you started out with this interval here, -5 to 5. And you would say, Professor Ron, that interval is symmetric about 0. Why? Because the distance from 0 to 5 and the distance from 0 to -5 is 5. So for instance, if you thought this, you could just write this down. And so we would think, you know, just kind of shading here, we'd say symmetric about 0, because the distance from here to here and the distance from 0 to -5 both being 5. But then you're thinking, oh, isn't that what you just wrote here? So then, of course, what does the interval notation mean? Well, it means x lives between -5 and 5. That's what that means. But if you have that, you automatically have this. So you can say if x lives between 5 and -5, that gives you the c, and you write this. So the key here is that when you go in the backwards direction, it's not the same, so to speak. You're unraveling things. What happens in calculus is you end up with a compound inequality, and then you have to move to an absolute value inequality to satisfy the definition maybe of a limit. So here's what I want to do. I want to give you a little recipe here. Here's a guide to create a symmetric interval. And I don't know that I've ever done this before. It's just that the question, I've done things around it, but since the question arose, I thought, why not say more about it and not have to beat you up with so many new things in calculus. So first of all, just say, if we just have some interval x1 to x2, the midpoint, this is what you learned in Algebra 1 and geometry. The midpoint of this interval, this is an interval, not an ordered pair, so think of this as an interval. How do we find the midpoint of the interval? Well, we add the endpoints. That is, we take the average of the endpoints, and that gives us the point in the center. I mean, if we add -5 and 5, 0 divided by 2 is 0, so boom, there we have it. So this is called the midpoint formula. Now, another thing that we want to be able to do is if we get the midpoint, that's going to actually help us, because now we can subtract the midpoint from all of the numbers in the compound interval and then create the symmetric interval. That'll give us the C. So here's an example. So then I'll say this will be the first part, and then 2 subtract midpoint from all terms in the compound inequality. And once you have that in the compound inequality, once you have that, you have something that looks like this, and you can go to here. So let's go ahead and do that. Oh, that didn't come out too neat. Let me rewrite that. Good old whiteout, the kind that you don't have to wait to dry. So now let's do it. Let's look at an example. So here's one I made up to give us some good numbers. And then of course, as you get more experience, you'll get less nice numbers. So now when we look at this, let's go ahead and take this into this form. So we have -3 less than x less than 7. That's a compound inequality. Every time you write an interval down, every time you write this, you mean this. I think everybody just is, you know, we get so used to writing these intervals that we don't really, I mean, here's what we think. We just basically go to the number line, but we don't always think this way. So be careful that you allow yourself to broaden how you write things. I mean, we all have to do it. We're thinking, how am I going to solve this problem? I've got to rethink the way I state things because I'm not seeing the way to the result. So now we've got MP. So I'm going to follow Professor Ron's recipe. So we have MP will be -3 plus 7 divided by 2. Sometimes the simplest things are the most difficult. And then of course that gives us 4/2, which is 2. Okay? So I've done this part. Now I'm going to subtract the MP from all terms in the compound inequality here. So I have -3 minus 2, x minus 2, 7 minus 2. Now that's going to give me the C. So I have a -5 less than x minus 2 less than 5. At least in the problem I'm trying to do. And so now it looks like this, but now what's in the center is x minus 2. So now we see that x has been replaced with x minus 2. We can go back up here and write the equivalent inequality with absolute value. So now we'll say here the C equals 5. So we have this. So the idea here is that often you'll start with this and then you'll break it up to get this. The beauty of this is that in terms of mathematical notation, this is very compact. It's very convenient. Convenient in the sense that it's a nice way to write a symmetric interval. So, I mean, you know, let's go ahead and do this. Let's go ahead and write it. So we have our 2, and then we've got what? 7, in this case, 7 and a -3. So I'll just kind of go over equidistant. So the idea here is that we have the distance 5 and we have the distance 5. So this is our symmetric interval about 2, whereas this was a symmetric interval about 0. Now I know this isn't very difficult and maybe right now not tremendously important to you, but when you get to calculus 1 and you start talking about the definition of a limit, this will be extremely important. And you will use this to where you're thinking, wow, calculus is just really a lot of arithmetic. But what's arithmetic? Arithmetic is algebra, it's number theory, and it's all the same. We just have to start respecting the numbers like we respect the letters. because that's, like I said before, where the gap has occurred. The gap is that we don't treat the numbers in an algebraic fashion. And because we don't do that, we don't see the beauty in the symbolic computation. And that's, again, like I said before, there was a time when the Euclidean geometry and number theory were taught as high school, middle school subjects. I mean, they were standard subjects, and they've changed a lot. And change is fine. It's fine, but I'm a big proponent of, like, if you want to add some new stuff, fine. Don't get rid of the old stuff. Just have some of everything. Now, so remember, when you're doing the BVs, it's like doing we're going to talk about this, the domain of a function. You have to look for boundary values. So the sign can possibly change where you have a 0 or an undefined. So just be careful with that as you work the problems. Don't forget the places where the expression can actually be undefined. We focused on the others, but it's an easy transition. The main thing with all of these problems, when you're doing the more complicated inequalities, is to get the 0. Once you have that 0, then the BVs and the sign test, or whatever approach you take, all make sense. Without that, it doesn't have any foundation. Now, what I wanted to do here is to kind of go through some of the basics of functions and get you thinking in a way that will be supportive for what we have in this class, and then also to remind you about some of the things that you did in college algebra that may have become a little bit rusty. So let's start with that. So we're going to have this is 2.1. Now, ladies and gentlemen, after 2.1, we're going to move to the 2.6, which is the section on the function transformations. I'll say a little bit about that today. So we'll get to use some of our basic functions that we used in college algebra to review those. So I'll go ahead, not too much longer, and post some of those sections. So functions. Let's start out with a definition. And this is pretty easy. You already know it, but I want you to be able to state it. So a function f is a set, it's actually a relation, but I'm just going to say a set of ordered pairs such that now what the such that part really turns out to be the vertical line test. But I want you to understand this from this set theoretic way because I want you to be comfortable with the concept. So for instance, if a function really, we know it's a set of ordered pairs because we graph functions. That's exactly what they are, sets of ordered pairs. So for instance, such that what? If A comma B, which would be an element of F, an ordered pair, if that's an element, and if A, C were an element. If this is true, that is, we have an element of F that has first coordinate A and second coordinate B, and we have an element of F that has first coordinate A and second coordinate C. I think what this will tell you is that if this is indeed a function, B must equal C. So based on what I've written here, that means every first coordinate, sometimes we call that the input, every first coordinate, sometimes this is called the input, is paired with exactly one second coordinate. which we often call the output. So the idea here is it doesn't matter if the outputs are all the same. Not very interesting. Constant functions do that, but we have to think of F as a well-tuned machine, so to speak. That is, when we put into the machine an input, we get out exactly one output. That is, there's no change. The machine works. It's kind of like thinking of your transmission. When you input D for drive, you expect to go forward. That means you have a transmission that works. So with that said, we'll say the set of first coordinates, is called the domain of F. Now, you know that from college algebra, and you probably took tests where you had to compute domains, and if you weren't careful, you missed it. But that's okay, because it's easy to make mistakes with domains. The set of second coordinates is called the range of F. So when we think about this, again, at least from a definition standpoint, you can make up all kinds of functions. You can make up a function to solve a problem in a science class. You might be making a new model and you come up with a function that supports your model. So functions really, when you consider them and you think about what they do to mathematics, I mean, when you step into pre-calculus, you really spend most of the time with functions. When you step into calculus, 1, 2, and 3, all you're doing is studying functions, because functions are this abstract object that relate spaces in mathematics. And when we do calculus, we talk about limits of functions, derivatives of functions, Riemann integrals of functions. Before the function was defined, mathematics was extremely tedious in the sense that nobody could really communicate with each other. And so the time came when the function definition were set into place, and many of the European mathematicians set the axiomatic ideas into place that now gives us what we do at present. So all of this nice notation we have was certainly not something that came up overnight, but we are certainly happy to have it. Now, let's just look at a function before we step into the formula approach. So let's say we have a function here, a set of ordered pairs. So we've got maybe 1 square root 2. We'll do a real value function with real input. -3, 0, and say 1/2, 4. And let's see, let's say, I don't know, 3, 4. Now, I've given you a function. That is, when you look at this, you can give me the set of first coordinates, and you can give me the set of second coordinates. And also, you notice that when it comes to all of these particular ordered pairs, we have every first coordinate paired with exactly 1 second coordinate. No mixing and matching with 1. We don't have like a 1 square root of 2, and we don't have like a 1, 3 down the way. So when we look at the domain, we can write that 1, -3, 1/2, 3. When we look at the range, we can say range of F. Sometimes we do that, or DOM of F. We'll have square root 2, We'll have 0, 4, and then we have another 4, but we don't have to repeat it. So what we can see here, at least from your knowledge of functions, this function doesn't have the one-to-one property because, again, the 1/2 is mapped into 4 and the 3 is mapped into 4. So there's not a distinct path from 4 back to the domain. So thinking about what you've done in your previous classes, that certainly is apparent here. But we're not really going to spend most of our time with functions that look like this, even though these are valid functions. Most of our functions will be formulas. So here is the focus here for this class and what you've been doing all along. We will have real valued functions, real valued functions of a real variable. So basically, this is going to drive us when we have formulas. That is, we know the input must be real, and we know that the output must be real. So let me just say this: input is real, output is real. And what's nice is these algebraic formulas give us really nice ways to generate this definition. When you have a nice formula, then you know if you put in different values for the input, you're going to get out unique outputs. Formulas are nice in that they provide one output. So they are great ways to actually understand functions. And that's really what we spend most of our time with. So I'm thinking when we look at something like this, you're thinking, well, that's kind of odd. And it is based on what you've done in the past. So let's go ahead and look at an example of something that's interesting here. So when you do your WebAssign, WebAssign will give you some practice with domains and practice with evaluation. And I'm going to say a little bit about ranges that we can actually do at this point. So here's an example. Remember, functions are your friends. So the more you work with functions, the better. So I'm going to write a real valued function of a real variable with a formula like this. Now, what's nice about this particular formula is that it reminds you of something you did in college algebra. I mean, you'd probably be okay with this. That's a rational function. We're going to go back and review these. You know how to graph these. These are functions that you spent plenty of time on, ratios of polynomials. And so the first thing we want to do is think about maybe what the domain would be. Now, when you compute a domain, you just basically have two ideas that you need to maintain, so to speak. If we have even nth roots like square roots or fourth roots or sixth roots, if we want output to be real, we can only take the even nth roots of non-negative inputs. So that's an important thing. So for instance, number one, we take even nth roots of non-negative, that includes 0, non-negative inputs. And 2, no division by 0. We exclude division by 0. Why? Because we don't know what it is. Division by 0 is undefined. So when you think about this, even though it makes our journey through mathematics a very interesting one when it comes to vertical asymptotes, which is really what defines division by 0, we don't understand it. We understand the behavior about vertical asymptotes. But when someone says, you know, what's 3 divided by 0? When you say, I don't know, that's the correct answer. That because you don't. So when we look at this, we see if we're going to compute the domain, we don't have to worry about any even nth roots because there are none. So if we're looking for the domain, let's just go ahead and write this in a couple of ways. We'll use the set notation. So we have to abide by 2. So we're going to say, at least formally, that x will be a real number such that 4 plus x does not equal 0. Now, again, we might have a fractional formula. Maybe the denominator is never 0. That's okay. Then we don't have to exclude anything here in part 2. But what this means is that now, maybe less formally, we'll just say x, assuming that it's going to be real, we'll just transpose x does not equal -4. So when you looked at this, I bet the first thing you said is, yeah, -4 is not going to work. That's like doing those equations when we clear denominators. For instance, if the only thing we found, you know, when we worked those problems were the prohibitive numbers, then we would say no solution. And that's always frustrating when you work hard and you find that the only values of x don't work. So when you look at this, you're thinking, okay, remember, this is what you exclude. So now what do you include? Everything else, -infinity to -4, union what? -4 to infinity. So when it comes to writing domains, WebAssign will tend to like the interval notation. There may be occasion where you will use the set theoretic notation, but here's the main thing, ladies and gentlemen. You must use the union symbol. When you say this or that, you must go over to the palette and use the union symbol. So basically, we have the entire real line except for -4. So you're thinking that's quick, but interval notation is convenient. And again, these are not numbers. They basically say any number greater than -4 will work. And this will always be greater than any number. This will be less than any number. They are not actual numbers. They just simply are symbols for the infinite. And so remember, when you do the infinity, you always close that with a parenthesis, not a bracket, because it is not a number. I'm trying to help you with the typing issues with WebAssign. Now, in cases where we can actually find the range, maybe we don't need a calculus class. That will usually be the case where the functions are well behaved, like they might be one-to-one, so we can actually solve things. But if you remember back in college algebra, you saw that you had the same degree here. So you're thinking ratios of leading coefficients, that would give you a -1. So you'd say, okay, y equal -1 is a horizontal asymptote. And you'd be exactly correct. That's a calculus result. And it's actually easy to learn in college algebra and pre-cal without all the bells and whistles, so to speak. But we would say in some situations where it's computable, we might say, well, can you figure out the range of this function? And how would you do it? So for instance, we can say, what about the range? You think, or at least your intuition is saying any real number except -1. Well, let me just show you a way to do that. Now, this is not always possible, but here's a possibility. So let's suppose that C is an output. So suppose C is a real output. The thing is that we could actually solve this as long as we can figure out a value in the domain that would be mapped into it. And that's what we're going to do. So now we're going to take the function 4 minus x, like we're doing an inverse problem, plus x equals c. And what I want us to do is solve for x. So if I ask you to do this, you will be able to do it. I'm not going to be horrible to you. That's no good. So there's a 1 there, right? So let's cross multiply. So we get 4 minus x equals c times 4 plus x. The WebAssign problems are good, but of course, Professor Ron looks at them and says, well, what else can we do with them? Most of them keep you tremendously busy, so we don't need extra. But here I thought this would be good. So we have what? 4 minus x equals 4c plus x times c. Now what we want to do is solve for x. So let's get all the x's on one side. And since we're lazy, let's take the negative x, add x to both sides. We'll do that, and then of course we'll take this over. So this will be xc plus x, and this will be 4 minus 4c, just transposing. Algebra is so useful, and we abide by it. So now, factor the x, we get a c plus a 1, and this is just a 4 times 1 minus c. Okay? So now we can actually solve for x. X equals 4 times 1 minus c divided by c plus 1. Okay? Now, when we look at this, this basically gives us the value for x that will map into c. That is, if we give c a value, then we know the element in the domain. But what this equation tells us, and this is where we have to think about it, is that if c were equal to -1, this is undefined. So there would be no x that would map into -1. So this implies c can never be -1. So this is kind of a roundabout way of saying, if I'm going to check to see what the range is it all real numbers, or is it what I thought? I have to leave out -1. So now this implies, or equivalently, the range, and we'll use y. Usually we use x for the input and y for the output, but you can use any letters. We have y element of r such that y does not equal -1. So now for the c not equal to -1, we'll just stick that in for y. And then we'll say, okay, well, that just means in terms of intervals, -infinity to -1, union -1 to infinity. Okay, so our intuition was telling us, yes, this is exactly right. So I don't want you to think that you can always do this. In some cases, you might need to utilize some calculus to actually figure out maybe like a relative extremum. In calculus with polynomials, you'll be able to find the peaks and the valleys, so to speak, using the first derivative test. I mean, there are all kinds of elegant methods in calculus that you will learn to further understand functions. But we can certainly do a lot with these types of examples. Now, here's what I want you to do. I want us to get a little bit of practice with some algebra. Now, here's an example. Let's just go ahead and use the same function, and let's get some practice with some algebra, and then we'll go back and do another domain and range with a function that you know about. So here's the function that we've just been analyzing, and here's a WebAssign problem. So we have f of x squared minus 4. Now, when you studied your compositions and all, you would often replace x with another expression. So this is exactly what we're doing here. So this just means replace x with x squared minus 4. So this is a very convenient notation when we work with the function notation here. It is a marvel of logic. I mean, we couldn't come up with something better. If someone said, I want you to change the function notation, we would disagree. We say, don't need to change it because it's just right. So now we'll just do that. So we'll have 4 minus distribute x squared minus 4. So we replace x with x squared minus 4 and use the parentheses because you know that good old distributive law will undo us if we don't. And then we have 4 plus, now replace x with x squared minus 4. So this is a common technique from college algebra, but it's good to review it because again, we understand mathematics through the use of functions. So now if we distribute, we have 4 minus x squared, and then minus the negative. We know that's the positive 4. And then, of course, downstairs, the 4 and the negative 4 absorb and give us x squared. So now we add like terms. So we have 8 minus x squared divided by x squared. Now, what I want to remind you of is that you'll have plenty of opportunities to do these kinds of algebraic computations. Don't look at them like, oh, I don't need to do this. Please work through them and practice this. These are skills that even though you may be very good at doing, I want you to get back into a good routine so that we have plenty of confidence as we work through these problems. Now, here's another example. This one is another function, and it's our friend. Professor Ron really likes the square root function. So we're going to change the independent variable to t. So we have the principal square root of t plus 1. Now, we don't have to do any elaborate computations like we did on the last problem. This, by definition, the principal square root is non-negative. So by definition, this is greater than or equal to 0. So we know what the range is. The square root functions, at least these that are unadorned, that aren't vertically shifted or whatever, start at 0 and they grow. Not really fast, but they do grow. So we can look at this and say the range of f will be all non-negative real numbers. Now, of course, it would be helpful to have some calculus here, but we've worked with this enough and we know what the shape is because someone told us, or maybe we plotted some points. But the calculus will further identify with this. Now, one thing that we want to do, as we had in the last problem, that is, remember, we take even nth roots of non-negative inputs, okay? So the only thing we have here is a square root, and then of course the input or the argument is t plus 1. So now the domain will equal all real numbers t such that what? T plus 1 is non-negative. Now again, very simple, but very important. And of course, the more complicated the function, the harder we have to work. If we've got square roots of more complicated arguments, then our inequalities, as we've seen in the previous problems, will be more difficult to solve. We may have to use the sign test. We may have to be very careful about what we do. These are easy, but don't think that they're all this simple. Be aware that with the square root, you will have to use the BV technique to move the problem to conclusion. So now we can just say, all right, all real numbers t, and just subtract 1, t is greater than or equal to -1. And that certainly makes sense to us. So now we're thinking, okay, well, this will be -1 to infinity. Well, now we're thinking, Professor Ron, this is just a left shift by 1 unit. That's a function transformation. So basically, we think, okay, if we start with t, square root, we do a left shift. This is just a little review of what we'll talk about more next lecture. Left shift by 1. So that means we replace t with t plus 1. And so if we think about this, let's just think about the simple points on the square root function that we always use to graph it, because we don't graph 500 points, we just graph 2 or 3 easy points, because that's all we need. We know what the shape is. So for instance, we could think of 1, 1, 0, 0, and then 4, 2, in just the standard square root function. So we have something like this, like that. Vertical tangent, like that. So this is just square root of t. We'll say y equals square root of t. And so now, of course, if we do the transformation, we just move those points, 0, 0, 1, 1, 4, 2, and we do the left shift by 1. This is the geometric impact. The algebraic impact is to replace t with t plus 1, but the geometric is just subtracting 1. So we get negative 1, 0, 0, 1, and 3, 2. So if we plot these, we have, well, of course, we know this. Negative 1, 0, 0, 1, and then 3, 2. But we already knew that we would have to start at negative 1 by our domain calculation. We get something like that. Y equal the square root of t plus 1. Now, of course, as we do more and more elaborate transformations, we'll stack plenty of transformations, and I'll give you the Professor Ron approach to do that. Stacking the transformations, you just basically unravel the formula and then apply the transformation so that the result is the original function. Of course, it's not unique usually, but again, it's like it's not unique in how you solve an equation. As long as you do it correctly, it's of no consequence to me. So the idea here is that even though this is simpler than the previous analysis, again, there's some very basic ideas going on here. So when we use the basic functions like the 1 over x or the x squared or the square root of x or the absolute value of x, we use those basic functions and transform them to get more elaborate functions, but we don't have to work hard because the transformations tell us what we're doing, and then we just move the points to get the new points. So the beauty of the transformation, function transformation, is really found out well in calculus. You don't apply fancy calculus to functions that you've done in this class. You don't need to. You might just want to verify, but you still continue to use these really nice techniques that you learn when you're doing calculus. That is, we take everything that we've learned and we keep doing it. We don't worry about undoing anything. Unfortunately, you're going to take all that you've learned and go through the calculus sequence. Then you're going to take all that from calculus and everything else before it and move on into linear differential equations, advanced calculus, topology, all of that stuff. So you're going to keep carrying more and more stuff with you as you work through math. And that's really what makes math challenging. It's like building a vocabulary in English or foreign language. You know, it's really hard because you have to not only learn new stuff, but you have to maintain what you already know. Now, what I wanted to do is an example where we compute a domain that has both a radical, an nth root, and division by 0. So again, this is a good WebAssign problem. So we have g of x equals, in this case, the square root of x. And downstairs we have 7x squared plus 6x minus 1. Well, My screen hasn't been lighting up, so I'm glad you can hear me. But in the future, if the sound ever goes out, just come in and do this and say, Professor Ron can't hear you, because boy, that's terrifying. That'd be like, you're on a phone call to a doctor and you need really important information, and it's like the sound goes out. That's really not a good feeling. So, uh, boy, I guess we'll never be to Star Trek, but we'll try to imitate it. Now, when you look at this particular function here, the square root of x is really not an issue. We're okay with that. But now we're thinking, what about the denominator? So let's look at the denominator and apply AC. So AC equals, so for instance, the question here, and let me write that first. I'll say compute domain. Compute domain. Now, like I said before, the formulas give us really infinite ways to write functions, because when you input a real number, you output a distinct real number. So these are great ways to generate functions, any kind of function you like. So now what we want to do is first apply AC. So we have 7 times the -1, and then we're like, wow, jackpot, that certainly sums to 6. So we can say the square root of x, and then we can rewrite 6 with the 7 and the -1. So we said 7x squared plus 7x minus x minus 1. Again, the AC method will never fail you. You will fail the AC method. I fail the AC method when I don't pay attention. So now we have the square root of x, and now we can factor the 7x, and that leaves us with an x plus a 1. And here we can factor the -1. So now we have g of x is the square root of x divided by 7x minus 1. That is, we see that 7 and -1 multiply x plus 1. Again, the distributive law. So when you're in a calculus class, you've got radicals, you've got variable denominators. You need to check this because, again, you may be interested in critical numbers. You may be interested in where the derivative is undefined and or horizontal. So you first need to figure out the domain. Now, when we look at this, let me do one more step, because we like to factor. Factoring is good, and let's reveal some zeros. So this one is fine if we're doing the BV technique, that's no problem. Let's just go ahead and factor a 7 out of this. So that'll give us an x minus a 1/7. So when we look at this, again, we have to replace the 1 here, the -1, with the -1/7 to compensate for factoring the 7. So when we multiply through, we get the -1 and we get the 7x. So now we can look at this and say, okay, well, we got an issue here. That is, we'll have division by 0 if x equals 7 or if x equals -1. So let's just go ahead and look at both of these. So for the first part, we'll say the square root of x. This implies that x must be non-negative. I mean, that's not very difficult. That is, we need a non-negative input. We need a non-negative argument for the square root to be real, okay? So again, this is always the case for even nth roots. Now, it could be that the radical's in the denominator, then we would have to have a strict inequality because we wouldn't want division by 0. So don't be careless and keep the 0 in if it's in the denominator, just as a warning there, just to make sure that you cover that. Now here, when we look at the second part, we have 7 times x minus 1/7 and x plus 1. Well, this implies, and we'll do this in the negative. We know that x cannot equal 1/7, because clearly that would make this 0, and we see that x cannot equal -1. Now, the thing is, this point doesn't even really matter so much, because around -1, this doesn't even make sense, because now what we're seeing is the square root demands that x be greater than or equal to 0. So this point is off in the twilight zone, so to speak. It's not even surrounded by any domain of the function. There's this big gap from -1 to 0. There's nothing. And then of course, if we keep going less than -1 down to -infinity, there's nothing here. So this is really, this poor -1 just got left out of the mix altogether. So we don't even have to consider that. So now when we look at all of this together, we know that x must be greater than or equal to 0. So we don't care about that. That's no longer relevant. So we'll just say not relevant. But this 1/7 is. So as we move from 0 on up, we have to exclude 1/7 and then carry on past 1/7. So this implies that we take 0 to 1/7, parenthesis, union 1/7 to infinity. And then of course, and resist the temptation to put a bracket around infinity. Remember, infinity is not a number. Infinity is just a behavior. So in this case, use parentheses with the infinity symbol. So when you're thinking about, ladies and gentlemen, when you're thinking about writing the entire real line, it's a very common notation to write script R, or we'll say -infinity to infinity, like that. Okay, so just remember, the use of the infinity symbol requires parentheses, because this means any number, as large as you like or as small as you like. Now, what I want to emphasize here is, even though a lot of what we do in this class seems to have no end or no real purpose, for instance, it's like, okay, so I know how to compute a domain, yay, that's good. But as you move on into other areas of your mathematical education and careers, you will see the relevance of all of this. Again, just remember that when you get to calculus, the work that you've done here will maximize the rewards in those classes. Now, what I want to do is look at some examples where we actually do some function algebra. Now, when I say function algebra, it's kind of like what we did when we replaced x with x² - 4. But I want to do a difference quotient type calculation. Now, you did these in college algebra, and when you take calculus with Larson, the Larson text, if you take a section with me, I also use WebAssign with Dr. Ron Larson's calculus text. It's kind of like the Stewart text you're using in pre-cal. It's probably one of the best and finest textbooks that's in existence now for these classes. I want to give us some practice with difference quotients, changing up the letters a little bit. Now, of course, when you get to calculus, you may use different symbols, but everything's still the same. So say we start out with a rational function f of x. Now, just for grins, let's go ahead and we know what to do. We can figure out the domain and range because we know how to work with the rational functions, especially when the degrees are the same. So just as a quick reminder, The domain would be all real numbers except -9, because of course -9 would cause division by 0. So I want you to check into that really fast, especially when the functions are more simply defined. So we'll be informal here. X such that X does not equal -9. So, and now I'll go ahead, I'll stop with the set theory and just use the interval notation, -infinity to -9, union -9 to infinity. Remember, get used to the union symbol. It's what you have to do to connect disjoint intervals. And now the range, we've already solved this problem. We've got that 1 there, the ratio of leading coefficients. We know that 1 is not in the range. We proved that with the last problem, and we don't have to do it again unless I just ask to see it. So this will be all y such that y does not equal 1. So the horizontal asymptote is y equal 1, and our proof shows that y does not ever assume that value. So we get -infinity to 1, union 1 to infinity. Now, like I said before, work through the problems where you evaluate functions, do as much algebra as you can stand. It will help you get better. Now, here's what I want you to compute. Let's compute the difference quotient. And we're going to use this notation. We're going to say f of a plus h. And sometimes Weber sign breaks these down for you. That's fine. You can do it that way. F of a plus h minus f of a divided by h. Now, what we have here is the assumption clearly that h is non-zero. Now, when you work problems like this, ladies and gentlemen, this is a difference quotient. Basically, this corresponds to the slope of a secant line. So this corresponds to slope of a secant line joining 2 points on the graph of a function. And those 2 points in this particular case will be a, f of a, and a plus h, f of a plus h. So when you take the difference in the y coordinates, you get f of a plus h minus f of a, which you see here, change in y. And then you get a plus h minus a, and that just leaves you with the h. So this indeed is the slope of the secant line. Now, in calculus, we would like to know where the tangents exist. That is, secants touch the graph of the function at 2 points. The tangent line touches the graph where it exists at 1 point. So this gives us a mechanism for computing the slope of the tangent to the graph of f where it exists, okay? So you're thinking, wow, do I have to do this every time? Well, no. The idea when you get to calculus, you're going to learn techniques that will allow you to differentiate functions of this type. So don't think that everything will be starting from scratch, but we obviously have to start somewhere. So let's go ahead and compute this for this function. So equivalently, we have now everywhere, and let me just say this, replace x with a plus h, replace x with a. Now, one thing that you see here that doesn't have anything to do with f is the 1 over h. Now, students will say, draw that line again and carry that all throughout the calculation. Do not do it. Just take the 1 over h and do this. It's kind of like, say, 2/3. Say you have 2/3. This is like saying 1 over 3 times 2. Do that to this. Just pull out the 1 over h and bring it to the left. And now we can focus on f of a plus h minus f of a, because that's where all the algebra is going to be. This guy's just going to hang out here until we can use it. Right now, move that particular variable to the left to get it out of the way, but don't forget it. Now, replace x with a plus h. So go up here, a plus h. And now here, x replaced with a plus h, a plus h. And then, of course, the 9 is just part of the formula right there. Okay? Now, if you don't like a and h, you can change it to any letters you want. It doesn't matter. These are just convenient letters. Now, minus, this says f of a. So everywhere we have an x, we replace it with a. So we get a divided by a plus 9. There. Okay? Now, all we want to do at this point is that we've got two fractions. Two fractions mean common denominator and simplify. So now we have 1 over h. Now, what's the common denominator? Well, it's just like having, boy, have we done common denominators. Symbolic computation. We need the factor a plus h plus 9, and we need the factor a plus 9. These are not multiples of each other, so we need both of them. So draw a nice long fraction bar, and we need a plus h plus 9 times a plus 9. Now notice we have the a plus h plus 9 here, but we don't have the a plus 9. So we say a plus h times a plus 9. And now we do the same comparison. Here we have the a plus 9, but we don't have the a plus h plus 9. So we say minus a right there times a plus h plus 9. So this is just right in red, common denominator. Common denominator. So again, you probably don't have any issue with this. If I were using numbers, you would be all uncomfortable. But numbers and the letters work the same way. So now, remember we have the 1 over h because, we just don't want to deal with it right now. So we've got, go ahead and do your fraction bar, a plus h plus 9, a plus 9. And now let's go ahead and multiply everything out. So we have an a times an a squared. We have an a times a 9, so that's plus a 9. Just write the 9 first, 9a. And then we have an h times an a. And then we have an h times a 9. Now over here we do the same thing. We multiply everything in the parentheses by negative a. So we have minus a squared minus a times h, or we can just write the h first like we did to the left. And then we have minus 9a. Now what you're seeing here is that pretty much all of these terms absorb. That's the beauty of this. And the reason that derivatives usually are much more tangible for students is that they remind them so much of this algebra that you do in pre-cal. When we get to Riemann sums and integrals, that unfortunately is a little bit harder, but we'll survive. So look, the a squares, they absorb. You can put boxes around things, you can put checks, but Professor Ryan does not want you to put a slash line through anything. Just don't do it. Unlearn that. 9a, negative 9a, gone. And the HA's the same. Okay, so does anything survive in the numerator? Anybody, does anything survive?
9H.
9H, excellent, Sydney, that's it. So good. So let's do it. We've got 1 over h, and we have 9h. And then this stuff we've been carrying around forever. You're thinking, Professor Ron, you could have just written that out to the left too. But, you know, let's not push it right now. I think you're doing really well. Now notice, now we've got, these are multiplied together. This factor, this is a factor, this is a factor, this is a factor. We see now that the h's absorb. And what does that leave us with? Well, the only thing that survives, the 9, and then downstairs, a plus h plus 9 times a plus 9. Now, this part is pre-cal college algebra. You're thinking, so how does the calculus fit into this problem? Well, here's the deal. We're thinking that h is basically converging to 0. That is, it's becoming closer and closer to 0, possibly from either side. And when that happens, this point and this point converge. They become the 1 point. So the idea is we're asking ourselves, in the limit, will this make sense? So now we think, let h, and this is the arrow, we use the arrow, approach 0. That is, in this case, we're thinking, when it makes sense, replace h with 0. Is it continuous? Replace h with 0. Now what that means in this particular case is that this is constant relative to h, this is constant, but that would just become a plus 0 plus 9. So we're thinking this will imply that we get 9, that's when we take limits, a plus 9 times a plus 9. So that's basically taking the limit of a quotient. And then we just get 2 copies of a plus 9 squared. Now, the idea here is that why do you start with limits first? Well, because I've been talking about h approaching 0. That's a limit. So you start calculus with limits, and then you move derivatives with 2 derivatives, which are limits, and then you move to Riemann sums and limits of Riemann sums. So everything turns out to be a limit in calculus. So you got to start with the basic concept of limit. So now here is the notation that you will use in calculus. This number here, 9 divided by a plus 9 quantity squared, is what we call f prime of a. That's basically the derivative of the function at a. And there are other notations for this. But I don't want you to think, well, we're learning calculus. No, this part right here is really calculus. I just want you to be able to go from here to here. At this point, if you want to think about what's going on here, where these 2 points basically converge to 1, that means that now where this makes sense, and you can see that this makes sense as long as a doesn't equal what? -9, because that's not even in the domain, you get a tangent line. So when we go back and look at the domain, we could never expect a tangent line at -9 because it's not even in the domain. And the same is true here. This basically says, based on what I've already taught you today, that we can always define a tangent line at any point in the domain of this function. We're done. So we'll just say a tangent line exists for all elements of the domain. So just like that's why I did the little calculation with the range before, because what we're seeing here is that it's pretty much turned out to be the same thing. If you think about that, let me go back to that. Remember when we got to this point and we said, okay, C equal -1 would never work. It cannot be in the range. So when we look at this, we see that A can't be -9. Well, that makes perfect sense because that's not even in the domain. So any other value of A works. So the idea of division by zero is actually one of the linchpins of analysis. It allows us to understand what it is we do with functions in general and how they actually behave near what we call these vertical asymptotes or black holes. You know, you think of a black hole as having infinite gravity. It's really what's going on here. When asymptotes exist, they're called singularities. And mathematics basically deals with these objects on a regular basis. We can't get away from them. We know that not all functions have these issues. That is, they don't have a possibility of division by zero. So we don't have to deal with it like with polynomials. So again, just remember that when we actually work through the domain and the range of these functions, especially the domain, you check out to see whether or not you have division by zero or even nth roots of negative numbers, because that helps you decide what the function domain is. Now, and what's going to happen in the next lecture, and I'm just going to go ahead and give you, we've got a couple of minutes here, just a preview of this. So I'll go ahead and put up some of the WebAssign for that. So this will be the next section. This will be function transformations. And since I've already kind of let the cat out of the bag, I'll go ahead and just give you the idea of what we're going to be doing. We're going to have always call f of x the parent function. Just like we talked about before, like the parent function, and that would be, for instance, like f of x equals the square root of x. We're going to talk about the standard functions like f of x equal x, f of x equal x squared, the standard functions from college algebra. And what we're going to do is suppose h and k are positive real numbers. That is, positive real numbers. So when we think about the transformations, the very first one will be the, and we'll go through this, will be the horizontal shifts. And I want you to think about this, horizontal shifts. That is, if we think of a parent function, that is, for instance, if we consider this, if we consider f of x minus h, what I want you to do is to go through this and think about what this means algebraically and what it means in the sense of geometry. So we have considered this, that is, f of x becomes f of x minus h. Describe this geometrically. That is, think about what I've said today and how does this move points. And I want you to think about this. Think about the fact that when we do algebra this way, and what it means to do this. And then when we think about geometrically and what it means. And so what I'm going to do is unravel this in a way so hopefully you understand that when we actually do this, this corresponds to a right shift by h. So I want you to think about this. In the previous class, I made the allusion to the shift, but I want you to think of what this actually means and how we can come up with the idea that it does actually mean that we have shifted the graph to the right by h. So think about what you're doing here and think about what it means algebraically, because this actual transformation and the horizontal compression and stretching are two anomalies of mathematics that tend to always give everybody an issue. And I want you to leave this class feeling comfortable about this. Now, as you work through what we've done this past week, this actually at least is something you've seen before. And of course, the word problems are something you've seen before. But take the opportunity to work through the symbolic computation, work through factorization of numbers so that you can have a clean equation. Work to setting up the word problems in a way that you move the equations to very user-friendly form and use the symbolic computation to complete the problem. Do the same thing for the inequalities. And for the functions, focus on notation, focus on range and domain, and focus on the function algebra. And then once you get tired of that and you've done all your work, go ahead and start thinking about this. Now, this is not easy. I'm asking you to do something that's probably going a little bit outside the box. But think about this and think about what you're doing algebraically and think about what you're doing geometrically as if you had to present this to one of your students that you were tutoring. Well, I'm glad you could hear me today. It's been a good couple of weeks as far as getting into the virtual classroom. And what I think is so good about this is that it allows you to focus on thinking about ideas that may not always be apparent when you're just looking at something by yourself. So I appreciate your attendance today, and everybody go get some rest, maybe get some lunch or whatever, and have a good day and help each other with your math. And of course, if you have questions, come to my conference hours or shoot me a message on WebAssign or email. Everybody have a good day.
Thank you. Bye.
Thank you. Bye.
Bye. Thank you.
Bye.
Thank you. Glad to have you in the class, Valerie.